You have probably slid a key into a door lock and felt a small, precise resistance as it goes in, followed by a clean turn that releases the door. A common assumption is that the key simply matches the shape, like a puzzle piece fitting into a hole, and that the lock opens because the shapes line up. That assumption is partly right, but it can be misleading, because the real action happens inside the lock, where you cannot see it, and it is less about a single shape and more about controlling tiny moving parts. What exactly is being blocked when the wrong key is used? How does the lock decide when it is safe to turn? And why can two keys that look similar behave very differently? A clear explanation comes from looking at how the most common lock type is designed to hold itself shut until a specific pattern is applied. The main misconception is that the key directly unhooks something. In a typical household door lock, called a pin tumbler lock, the key is not pulling a latch open. Instead, it is lifting a set of pins to a very exact height, so the lock cylinder can rotate. The lock has two main pieces, a fixed outer housing and a rotating inner plug. The plug is the part the key turns. When the plug cannot rotate, the latch mechanism connected to it cannot move either. Inside the lock are small stacks of pins sitting in drilled holes. Each stack usually has at least 2 pins, a key pin on the bottom, which touches the key, and a driver pin above it, pushed downward by a spring. When no key is inserted, the pin stacks sit partly in the plug and partly in the housing. That creates a physical blockage at the boundary between plug and housing, called the shear line. As long as any pin crosses that boundary, the plug is mechanically jammed and cannot rotate. When you insert the correct key, the ridges and valleys on the key's edge push each key pin upward by a specific amount. If the key is correct, every key pin and driver pin boundary lines up exactly with the shear line. In other words, the split between the 2 pins lands right at the plug's outer edge. Once all stacks are aligned, nothing blocks rotation, and the plug can turn smoothly. With the wrong key, even one pin stack remains misaligned, meaning a pin still crosses the shear line, and the plug stays locked. This is why the shape match idea is incomplete. The key does not have to fill the hole like a mold. It has to set a series of heights accurately, like dialing several tiny measurements at once. That also explains why the key can still insert with the wrong pattern. The keyway, the groove shape that guides the key in, mainly prevents completely wrong blanks from entering. The actual security comes from those internal pin heights, not from the outer outline. The process also explains a familiar feeling. When a lock is slightly sticky, you might jiggle the key, and suddenly it turns. That often happens because friction and small manufacturing tolerances make the pins hesitate. A small change in pressure can help pins settle at the shear line. It also explains why a worn key sometimes fails. Over time, the peaks on the key can wear down, lifting pins a little less than they should. If a pin is even slightly too low or too high, it crosses the shear line and blocks rotation. There are edge cases and variations. Some locks add extra sets of pins, sidebars, or angled cuts to resist picking. Some use wafer tumblers, common in cabinets and older cars, where thin wafers align rather than pin stacks. Some use disc detainers, where rotating discs must align. But the core design idea is similar. The lock stays mechanically blocked until internal parts align to a narrow permission line that allows movement. This system exists because it is reliable compact, and easy to manufacture at scale. It turns security into a simple mechanical test. Can the user produce the correct pattern of internal alignment? In everyday life, understanding this makes it clearer why lubrication helps, why worn keys cause trouble, and why duplicates must be cut accurately. It also clarifies what lockpicking is actually doing. It is not forcing the lock, but trying to align those internal parts one by one, so the shear line clears. In simple terms, a pin tumbler lock stays locked because pins physically block the cylinder from turning, and the correct key works by lifting each pin stack to exactly the right height so the blockage disappears. This matters because it replaces the vague idea of matching shapes with a more accurate picture of how small tolerances and wear affect security and reliability. If there are other everyday mechanisms you want explained in this calm, step-by-step way, you can suggest them